does?
Oh, it's all the time.
I've never
I've
tried.
No. I like it. I think I get
It's 5 pounds.
It's like $10 for a few.
Oh, it's a class. Oh, it's so
We have to go to the class thing.
Potato.
Yes. Yes.
Not like
So,
Laura. Maybe this big physical.
I just. Hello? I don't even know what
Are you there?
Oh my
Just
God.
saying about here.
Are you dead?
Are you bad?
Have you seen Smurfs? He probably hasn't. Have you seen him?
You should very much watch Smurf. And watch Bob the Smurf.
He is Papa Smurf.
He loves you those favorite. Yes.
Mr. Potato, you are Papa Smurf.
Really?
Yeah.
I thought they were rather short.
Okay, but like you remind me.
Talking about looks. I know you're not blue. I know you're not blue.
I didn't say you were built like a Smurf. Just remind me.
You feel like.
Sorry.
I'm sorry. I didn't think about
So
that.
you're not. Built like
I'm built like a
I'll
smooth.
find a Smurf.
Yeah, you remind me of
I look like the
Smurf.
little girl Smurf with the little Smurfette.
Facial.
Smurfette? Yeah, that's her name, Smurfette.
Yes.
Okay, I'm
It's the
Smurfette.
general
That's what
resemblance.
actually no,
Is
it's
it
not.
like
I have one
little white beard?
Yeah, it's a stubble.
here.
I haven't seen Papa Smurf in a while. Hold
Here
on.
we go. I found him.
Oh, no, they
What
don't.
kind of chemical, what's going on here on the board? What have I written up here?
That's a chemical equation.
Yeah, be specific.
Combustion.
The combustion of
Read.
methane.
Oh, very good. It's combustion methane, right?
Yes,
Very
sir.
good. All right, so it produces heat, correct? All
Sorry.
right. Produces heat, okay? If we graph the energy of these reactants and products in an overly simplified way, we would come up with a graph that looked something like that. Okay, and there's a loss of energy as this reaction proceeds to reactants to products. So it's those three reacting substances, I say three because there's methane and 2 oxygens, right? As they do whatever it is they do to become a CO2 and 2 waters, there is energy lost, right? Okay. Now it's not going to happen in one step. There's a lot of different bonds to be broken and formed here that we learned in the last unit. They're going to happen in individual elementary steps, right? 2 or 3 or 10 or however many there are. Okay. But we can think of it as one step for simplicity's sake here. The energy that's going to be lost there is known as the enthalpy. Or actually, the change in enthalpy, I should say. So let's, side note here, I'll do a lot of those today. Enthalpy is the heat content of a system. I'm going to write that definition down. Okay, it's the heat content of a system. But there's no way to measure the heat content of a system. So I can't take this desk and figure out how much enthalpy is in this desk. That's not a thing. Okay, I couldn't take a methane molecule or a mole of methane and figure out how much heat is in there. What I could do, though, is I can figure out the change in the heat or the change in the enthalpy when that desk or this methane undergoes some kind of change, chemical or physical change. At that point, we can measure the difference in before and after. So in this case, we don't have any idea how much enthalpy is in the methane or the oxygen molecules. And we don't have any idea how much methane is in the CO2 in the water after the reaction. All thing we can know is the difference in the two. Okay? That makes sense? All right. Think of it this way. If we had a classroom of people here in this room, There's a classroom of people across the hall, right? And if you stood out in the hallway and saw 3 people walk out of this room and into that room, you still don't have any idea how many people are in here, right? Or how many people are over there, but what do you know?
There's
How
three
many
less.
went?
There's 3 less here and 3 more over there, right? It's kind of the same number. Okay?
Good analogies.
You really are. Like, it really helps sometimes.
Yeah, the house thing and that, those were.
Oh, yeah, that
What was the house thing?
The house, where
Like
it's
the
like.
activation energy is like the price of the house that doesn't change.
It doesn't change, but like you can overcome it easier if you're getting paid more.
Ah.
Oh,
yeah.
I liked your analogy when you were talking about like walking through the door. You remember we were talking about
Half-Life.
I
Yeah.
don't think it was.
Oh, yeah, and
This
somebody
It
got.
was heavy, I remember this.
We're talking about the half-life, like how it's like
Yeah, yeah,
three
we're
people,
going.
how many people will be left in the classroom after so much time. It's Half-Life. I just don't remember the time.
Remember enough of it, hopefully.
Yeah.
All right, so
Yeah.
this whole unit is basically about enthalpy change, okay? A little bit more terminology. This one is losing heat, right? So this particular reaction has a delta H that's negative, less than 0. It's some kind of negative number, all right? We call that exothermic.
So that it's gonna feel hot.
Yeah, it's going to feel hot. That usually confuses people. So when we talk about these numbers, unless you're told otherwise, we're talking about the system versus the surroundings. This is the system. Okay? So there's a system and a surroundings that make up a universe. Now, there's 2 types of universes in science. There's the capital U universe, which means every single thing that exists everywhere. Okay, that's no point in including that in all of your calculations and laboratory experiments. Who cares, right? Lowercase universe is the immediate area that you're dealing with. So like if we were burning some methane back there, one of the Bunsen burner burns methane, right? So if we turn that on, the system would be the methane and the oxygen, okay, and the CO2 and the water that's being produced. The surroundings would be this room. We would feel the room start to warm up, right? Feel the heat, okay? The oxygen is predominantly being taken from this room, and the CO2 and the water is being put in this room. There would be no need to consider really anything outside of this room, right? Because we're not using oxygen from the hallway. That means we used up all the oxygen in the room and we all died, so we wouldn't care anymore, right? So we're not using oxygen really from anywhere else. Vapors are not going anywhere else. So we would consider the Bunsen burner chemical reaction and the air and the table and the stuff in this room is the surroundings, and that all would be a little lowercase universe. There would be no need to think about anything outside the room. Okay. All right. So the system is putting off heat. The system is losing heat to the surroundings. If you go back there and put your hand near that Bunsen burner, your hand is now part of the surroundings, right? And you're going to feel that heat come into your hand, right? So the heat's coming out of the system and into surroundings, which are your hand. And if you get too close, in other words, too much heat's coming into surroundings, and you get a nerve reaction. Your brain says you can hinge, right? Fire. Okay. So that's exothermic. Now, if it were positive, what would we call it? Endothermic. So the opposite of that is endothermic. All right, so that's just the terminology we need to use. Negative delta H's, losses of heat, are exothermic processes. Be chemical or physical processes. Remember that boiling, melting, all those phase changes are physical stuff, right? This is a chemical change. The gain of heat, so if a system absorbs heat, what we would feel is getting cold, right? So there's a chemical reaction going on and we grab the beaker and our hand feels cold. It's because heat is coming out of the surroundings, which is our hand, and into the system because it's absorbing heat. That would be a positive delta H for the system because it's gaining heat positively, which we would call endothermic, heat going into it.
What was that definition enthalpy you said earlier?
Heat content. How much heat is in something. But we don't really know how to measure that unless it's moving around. Okay. A couple of different ways that we might find ourselves having to calculate this stuff, okay, come up with these numbers. One is calorimetry. These are in no particular order, by the way. And I don't remember which ones we did or did not discuss last year. It depends every year is how much time we have, which how many needs to cover. So I don't know if we did or not. So we're just going to talk about all of them as if we hadn't talked about it before. All right, no particular order, but first we're going to talk about is calorimetry. Calorimetry is this little process. Try to draw this. Let's just do a sort of a crude thing here. We've got our little Bunsen burner, right? Okay, so here's our little fire, right? And we heat we may have done this last year. We heat a can of water. We do that last year?
No, I can.
Did we heat some water? Did it burn a
Remember learning this?
Cheeto
We were
or
in Miss
anything?
Dearman's class.
Yeah, but we were
We were not in the room?
We were in Miss Dearman's
Test
class.
going
I
on.
was in the fields.
Oh, yeah, you taught us.
I don't know. I don't know. It was for something.
What was that for?
Were they taking an ACT or something?
They were taking
I just remember
something.
them
We were
sitting-
there for a few
You were
days.
just sitting on the desk, like teaching. You're like singing. Maybe I'm true.
Very possible. All right, if we took that Bunsen burner back there, okay, and set a can of water on top of it and turned it on, right? And we measured how much methane was being burned. So we had some kind of gauge on the hose that could tell how much methane was coming through there, right? And then we could measure the temperature change of that water, right? That water really hot, right? The heat coming out of this methane is going into the water. All right. Now we're going to make a bad assumption every time we do calorimetry. We're going to make a terrible assumption, and that assumption is that all the heat coming out of here goes into there. But where's some of it going to go? It's going to go into the surroundings. Okay. Now, if you use an actual we use it, this is still a cheap one, it doesn't work great, but if we use an actual calorimeter, what you got here is a deal with, it's insulated, you put some water in here, you can run a chemical reaction around it, do whatever, you've got a thermometer, it's got it sealed up a little bit, right? It's still gonna lose some heat, but not near as bad as an open flame. You know, that's very inefficient, but gives the idea anyway. So what we would do is we would measure the temperature change of that water. All right, and then there's an equation. Okay, this is the equation we got to know. Q equals MC delta T. Jot this down what all the letters mean. Q is heat. It's going to be measured in joules. Joules. Because H will be normally measured in kilojoules, just 1,000 joules. M is mass. You measured in grams. Right, C confuses people sometimes, so kind of think about this a second. C is called the specific heat. Right? It is a number, okay, for every given substance has its own specific heat, and it's essentially how much heat is required to change the temperature of something. So water, for example, is very difficult to change its temperature. It takes a long time to boil a pot of water, right? Compared to how long it takes for the pan itself to get hot. So metals have very low specific heats. Water has a very high specific heat. If you think about boiling a pot of water, right? As soon as you turn the stove on, in 5 seconds, you can't put your hand on the stove, right? Because that's metal. It gets hot really fast. As soon as you put the pan on the stove, in another 10 seconds, that pan's going to be too hot to touch. right? Pour 2 gallons of water in that pot. You can stick your hand in that pot of water for several minutes until it starts to become uncomfortable, right? It takes a long time to get that water to change temperature. It's not really a time thing, it's the heat and how much harder it is to get those molecules to vibrate faster. Okay. So that's a number for every given substance has a number. The only one we need to remember, and this is on the formula sheet, it's just one of those things that chemists ought to know. The specific heat of water is 4.18 joules per gram Kelvin. That's just a number you ought to be somewhat familiar with.
What does the Q stand for?
Heat.
Oh,
And you can choose
What did you say delta H was?
measuring tool. All right, delta T, that's change in temperature. You can get away with leaving it in Celsius because you're subtracting. Okay, subtracting Kelvin and subtracting Celsius gives you the same numerical answer. But I would highly recommend, because of mistakes that can be made later, that you get into a habit of always putting stuff in Kelvin. It's as simple as adding 273, right? And sometimes you have to, if you're multiplying, you have to put it in Kelvin, or you're going to get the wrong answer. If you're subtracting the two, it doesn't really, it technically doesn't matter, but it's just a good habit to get into. Just always put your numbers in Kelvin, your temperatures in Kelvin before you do math. Okay, so all that being said, if we measured the mass of the water that we put in this can before we started this little procedure, okay, and we know that it's water, so we know that C is 4.18, and then we measure the change in temperature with that little thermometer we stuck in the can, okay, then we can calculate the amount of heat that was absorbed by this water. Okay, simple multiplication. All right, now, then we make the very bad assumption that that's all the heat that came out of that burning methane. In this case, that's not going to be true because we lost a lot of it, right? But if we did this in a calorimeter, or especially a really good calorimeter that was truly insulated, okay, then it would be a pretty good assumption that that's all the heat that came out of here, all right? So what was endothermic for the water must have been exothermic for the methane, okay? And then we can, from that, we can calculate the enthalpy change of that reaction by doing this right here. Delta H.
Which one's the one?
Oh, this thing.
This one's not the one?
No.
Okay.
Okay.
Oh, we're good.
Now, that's a true statement right there, that delta H is equal to heat divided by moles. Moles of the reaction, what that says. That's a true statement. There won't be any other situation on the exam, but you just need to know. That's a true statement only if it's a constant pressure system. All of our examples will be constant pressure systems, which means there's no cap on it. There's no top, no sealed up reaction, okay? If it's not constant pressure, okay, it would be a constant volume system, and that's called bomb calorimetry. And that's when you do it in a sealed container, which by definition is a bomb, which are very dangerous things to deal with. So therefore, we don't ever do them in high school, and therefore they don't ever put them on the test, because then people would feel obligated to try to teach it, and then obligated to try to demonstrate it, and then people would die.
Yeah.
It's, no.
Want to do it outside?
No.
Hey,
So the rule for high school chemistry and freshman college chemistry, and even beyond that, you really, really know what you're doing, is that you never, ever, ever, ever seal anything. You never put a top on anything, okay? But when you do that, you by definition have made a bomb. So it's gonna blow up. So all of our questions, all of our demonstrations, anything that we deal with at this level will be a constant pressure system, which is not bomb calorimetry, but just regular calorimetry. and that equation applies. So let's go back through what we could do here again. By measuring the heat that was taken in by this water, we think we know the heat that was put out by this chemical reaction, okay? If we know how much of this reaction, how many moles of this methane we burned, we have to measure that in some way. We have to have some kind of gauge on the pipe, right? Then we could do a heat divided by moles, simple little math calculation, and that would give us the enthalpy of that reaction. You can do that for any chemical reaction, okay? So basically, if you're measuring the temperature change, okay, then you're measuring the heat in calorie by, that's all that for heat, okay? So you're measuring this calorimetry, heat measurement, right? If we weren't English, we would think of that as measuring of heat, which would make more sense than what it seems like. Anyway, so we're measuring the heat, okay, using this equation, and then we can calculate the enthalpy change for whatever the chemical reaction is. Okay, one way to come up with delta H. All right, there's a couple other ways. Another way is using heats of formation. Sometimes doing the chemical reaction in a calorimeter is not really a viable option. It might be dangerous. It might be hard to get the substances. The main reason it's not always the best way, though, is that a lot of chemical reactions, especially those that are a little more complicated, don't produce the same product. There's multiple pathways that it can take, especially organic chemistry, right? You can mix things together and you basically have 2 or 3 different possible chemical reactions that could take place with 2 or 3 different sets of products. All right, so you don't really know with different stoichiometries and everything. Okay, so that becomes not really viable to do that in a calorimeter. It's usually what's called heats of formation. Okay, so not every well, probably just about every known substance that's been used for anything over the decades, they have calculated the heat of formation. So there's a thing, let's just use these as examples. Okay. So carbon and 2 hydrogens produces methane. We would call that a synthesis, but it's a little more precise than that. That's a formation reaction, okay? That has a delta H value equal to some number that you look up. It will be given to you on a test question. Okay, they will give you a table of numbers. All right. Carbon dioxide has a formation reaction that has a certain delta H value. Water has one. What did I do that looks a little unusual right there?
You don't have a whole number though.
Yeah. So formation reaction, and sometimes they will ask you have seen test questions where they say, write the formation reaction for this compound, right? And all it is the synthesis from its, here's the key term, constituent elements. Constituent elements. Where else have you ever heard the word constituent? I'm thinking government yet?
Constitution.
It's close.
Constituent.
All right. So politicians have constituents, okay? So, like, for example, we live in Alabama Congressional District number 7, okay? And our congressman is Mike Rogers, right? We are his constituents, okay? We are the people that make up the 7th Congressional District, all right? As a citizen of Alabama, you are each of our 2 U.S. senators' constituents. We all are the people who make up the state of Alabama, right? So what are the constituent elements of methane? What 2 elements make up methane?
Carbon and
Carbon and hydrogen, right? How about CO2?
Carbon
Carbon
dioxide.
and oxygen. How about water?
Hydrogen
Hydrogen and oxygen, okay? But the way that enthalpies of formation are recorded is the enthalpy change in the formation of 1 mole of a substance.
Mr. Cato, can you send Marisol to the office?
Can,
Thank you.
I think you're supposed to be gone. Wow.
maybe so, who knows? All right, so the way, by definition of an enthalpy of formation, okay, is the enthalpy change of forming 1 mole of a compound from its constituent elements. So you have to balance the equation so that the compound has a 1 in front of it. Okay? If that requires using a fraction somewhere else, then that's what you have to do. Okay?
So why is there 2 oxygens in the reactants, but only 1 product?
Diatomic, right?
Oh, because I put the half in front of the wrong thing. That's why.
Just in case.
There we go. Sorry. Put the half in front. My fault. All right, so enthalpy of formation definition, okay? The enthalpy change of the formation of 1 mole of a molecule from its constituent elements, okay? Now, what do you do with those numbers? Okay, well, there's this crazy looking equation. It's not near as bad as it looks, okay? But here's the equation that we'll need to use. Anybody know what those big Greek letters mean? Those are sigmas. What do they mean? Math class, anybody? Sum, right? Means to add everything up, right? Okay. So this equation, all right, says you're going to take, let me put a little, enthalpy of formation of products. This is the enthalpy of formation of reactants. Probably would have put a little F right here. Each of those. All right, so if you have a table, which you would be given on a test question, that contain the enthalpies of formation, for in this example, methane, CO2, and water, okay, then I could apply this equation. You add up, summate, add up all of the enthalpy of formations of the products, okay, which would be 1 carbon dioxide and 2 waters, right? Add those numbers up. And then subtract from that the sum of all the reactants, which would be a methane. Does anybody notice that I've skipped oxygen? Yeah. So why would I skip? Why am I leaving oxygen out?
Because is it
There you go.
because it's like not really then it's like just because it's invested.
Hold on, let's guess.
What's that
Don't tell
definition
us.
of a formation? What's the definition of enthalpy of
You
formation?
went too fast. You
Some
said
sort of-
1
Like
mole
4
of
times
something.
on purpose.
Oh, it's just
Some
oxygen.
constituent 1 mole of something.
Constituent, okay, so it's
Really?
the enthalpy of formation of a compound from its constituent elements. Oxygen is not a,
Why not?
it's not a compound made from constituent elements,
Oh.
right? Because it's just oxygen, right? So you don't make oxygen from
What makes
other
something
elements.
that's
It's not like I take lithium and boron and make oxygen,
What?
right? That's not a thing. Okay?
What makes? I'm confused.
It's a pure element. So by definition, you don't make elements from elements. Okay? You make compounds from elements, right? Okay, so jot this down because they won't tell you, they'll purposely leave this off and try to confuse you if you don't know this little fact, okay? All right, is that the enthalpy of formation of a pure element is 0. Okay, that's important to know because you're going to be looking for that. If you don't know that, you're going to be trying to find a number that they're not going to give you because they're going to expect you to know that the number is 0. Enthalpy of formation of a pure element equals 0. Second thing that's got to be brought back to elementary school, besides learning how to do basic arithmetic.
You said
It's
it's too fast.
dictation.
You said
Yeah.
it too
No, I
fast.
don't
I
say it.
don't.
Yes, you did. You said it too fast, and you started talking about
Say it
something
quick.
else.
They gotta say it pretty
Like,
fast.
Say it too fast.
Will
I say
you,
it too fast for y'all, but I don't say it too fast.
will you understand?
Well, I was
that you
writing
teach
something
this
else down
every
while you were
year?
No,
First off-
but y'all, it's because y'all don't write fast. It's a learned
I
skill.
don't know.
It's a learned
I was
skill
thinking
that y'all haven't been taught.
They got us typing essays.
Yes.
Fucking
Type too
nitro
much
type
stuff,
of talking.
Then you don't practice taking
I don't
dictation,
know.
which is something that you should have learned how to do in elementary school.
They never taught me cursive.
They quit teaching.
This is laughing.
They quit teaching people how to do that, and you can see the detriment of it, right? When you're trying to take notes in a real class, y'all can't write fast enough. And there's practice. Some reason y'all can't do math fast enough because you didn't practice it. But anyway,
Yeah, they used to put us on nitro type.
Huh?
They used to put us on nitro type.
he's mad.
It's a game and you have to get high, really fast.
He's tired.
And then we played Prodigy too.
Yeah, see,
Because it's math.
but y'all didn't learn how to do stuff that's practical.
That's what I'm saying. Why don't we learn more stuff in high school that we actually
That's a good question.
like? I'm for
That's what
real.
all that career prep stuff's supposed to be.
But that's techie stuff.
Yeah, that's not like actual.
Yeah, literally, like, all
It's
the-
just how to use.
All we do
different,
is
like-
typing.
All we do is
Career
spreadsheets.
Hey,
Like,
talk
yeah, all you
about
do is learn how to
English.
use a
Yeah.
spreadsheet.
And
Did
learn
that
how to
do
type.
that? I thought career prep did that.
No.
We did. I mean, I've
It
learned.
teaches you
I
how to
mean,
use a spreadsheet.
it
goes over some,
Oh,
just
Oh,
a
it's
little
that
bit, but
kind
not.
of
It
stuff.
goes
It tells
over-
you how to write a
Do your
resume,
taxes.
but I mean, that's.
It goes over like taxes and stuff.
It goes over taxes.
And a little bit.
Not
No,
just a little.
Career B.
Well, me and Elena aren't there yet. What are we doing right now?
So what practical information are you wanting to know? Taxes? Like how to do your
No,
taxes?
just like I don't
Right,
know.
some of
Like,
this stuff was
how I
really
can walk out of here like knowing I'm gonna be a successful adult.
We don't know how to teach that.
How?
prepare all students for a successful life.
He's not Mr. Reed.
I'm just saying. Like that's our school motto. Then like.
I guess, I don't know, we did income taxes back in high school.
But like algebra 1 with finance,
Huh?
like algebra 1 with finance,
Yeah.
that's all like math you need to know. About.
Maybe,
No idea on that.
teach a life skills class.
So y'all just want life skills.
Yeah,
I mean, because at this point, what else do we?
because like
We
I
don't want to be
don't
crying
know.
on
It's
our
just
parents'
like
doorstep asking them to help us when we're
And
like
this
20
world's
years
so
old
broken,
trying to
like,
figure out how to get an apartment.
That's true.
It just doesn't seem like that's stuff to do. Like, I don't
What?
understand how people can't just figure that out.
to you.
Like it should be self-explanatory.
Yeah, that's pretty simple.
Do you know what our
I mean, they
generation
kinda
is?
Do you know what I'm doing?
I mean, like buying a house, I mean,
Mr. Cato, this is the same
You
group
bought
of
yours
people.
today, don't teach
I
us
did
what
learn
you need
about
to know to
multiple.
buy
I'm
a
not
house.
saying
I
someone
can
buy a
figure it out.
You say it should be self-explanatory. This is the same group of people. Now, I know it was one specific person that it applied to more than anyone else. This is the same class of people. We had to go in detail about the difference between Indians and American Indians.
Oh,
true,
That
so
true,
bad.
noted,
Oh my
noted.
God. That day I went home and was like crying to my parents because it was so funny. They were like, there was somebody in your class, in your advanced class that didn't know.
Drew a map of the world on the board and explained it.
Yeah, I came in that one day, wonder why
I
you
know
were
it's
asked.
from learning this a generation before us.
In my we like for example, I never had to memorize the states and capitals.
I never had
But
to
see,
memorize.
that's not that needed, I mean,
I never even had to fill out.
so here's the two things that
I
people, complain about, that school never taught me how to do, is that at school didn't teach you how to do taxes, the school don't teach you how to take out a loan and or buy a house, right?
Okay.
So here's the thing about those stuff. Here's your life skills, right? Okay. Number one, very few people do their own taxes. Okay. Very few people. I do my own as in the past. Okay. But very few people do. You call the tax company, the H&R Block or whoever, right? And they're going to do your taxes, especially if they're complicated. If you got a business or something, unless you have an accounting degree, you're not going to do your taxes, right? It's foolish to do it because you're going to mess them up. You're going to cause yourself a lot of problems. It's so much better just you go pay somebody to take care of it for you, right? So you don't have to know. You need to know the concept of taxes, which they teach that in your government economics class, right? Is that your government is stealing your money from you, okay? You need to understand that the government is stealing your money, all right? You need to make sure you have that concept. And all you're doing when you quote, do your taxes, is you're settling up with the government and see who owes who what at the end of the year. Because you pay taxes all year long. Maybe you didn't pay enough, maybe you paid more than you owed. And that's all you're doing in the spring of the year, is you're doing an accounting of how much was I supposed to pay versus how much did I pay. And if I paid too much, they'll give me some back. And if I didn't pay enough, I got to pay the rest. Okay, so that's all you're doing in your taxes. The actual how to fill out the form stuff is really, I mean, if you want to go figure it out on your own, knock yourself out. But 95% of people pay to have it done, right? Just like buying a house, okay? When you get ready to buy a house someday, you're going to do the obvious thing that 99.9% of people do when they get ready to buy a house. And they're going to call a realtor, somebody they know, or somebody who's signed or advertised that they've seen, right? Okay, and you're going to call them and say, I'm looking for a house. And they're going to tell you everything to do.
It's like you're shopping, like you're in a store and you're shopping for something.
Yes, they're going to take, and as far as like, how do you pay, they'll explain it to you. That's their job. And you're going to pay them to do that for you. You're going to pay them 6, 8, or 8% commission on the sale of the house. And part of what they're getting paid for is to literally walk you through every step-by-step process, including they're going to send you to a mortgage company or a bank and say, go down there and tell they'll call them for you and say, hey, I'm sending you somebody, so-and-so, and they're trying to buy this house for this much money. And that person's going to explain it all to you and basically say, sign here, 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 here. So like, I don't know that it would be in the best interest of high school to spend a lot of time like trying to explain the details of
I don't want to learn that, but
mortgages
like,
and income things.
I feel like,
You'll figure it out.
I don't know.
I feel like I'm not ready to have the dollars.
Yeah, it's not even so much that, like, I'm trying to think of what I feel dumb.
I think y'all need more career advice.
Yes.
I think y'all need
I
a
feel
lot more of
stupid
that.
about things that I feel like sorry.
Like how to get a job, like how to.
Yeah, okay, like for example, the seniors, at some point every year,
Clinical
maybe they've
project?
already done it, I don't know. They will have this big deal in the lunchroom. Y'all seniors, y'all done this, seniors? Y'all done this yet, where you make this little poster about what you want to be?
We're doing it right now.
Working on it right now? Okay, well, I'm gonna go down there and walk through that every year, because I always do, right? And I'm on camera, and I'm glad somebody will hear this. And I don't do the math, so I don't know the percentage. There's a pretty good percentage of people in there who you can tell have no idea what they're talking about when they do this career day thing. They put some gibberish on a poster board that they looked up on the internet the night before, okay? Because half the people down there, not half, a large percentage of people down there say they're going to be engineers, okay? And most of the ones who say they're going to be engineers have never taken mine nor Coach Buzon's class.
Whoa!
You're in his class
Right.
now.
I know, I said the vast majority of them who say they're going to be engineers have never taken either of our classes, okay? Which means there is no way that you're ever going to be an engineer, okay? So you made a poster about being a chemical engineer, right? And you said you're going to be a chemical engineer. You obviously have no idea. And I don't say this, I just smile and nod and walk on by, right? But there'll be dozen or more of these kids who've got these posters of these careers. It's obvious they don't even know what it is, okay? Because if you've never taken chemistry and calculus, you don't have any idea what engineering is. Like, you don't even know what you're talking about, but that's your career. Like, so we're obviously not really educating people about careers, right? If people who took environmental science and algebra think they're going to be a mechanical engineer, because you're not, right? Right? No way, not happening. So I don't know what you're going to be. There's lots of other things you can do, but it ain't going to be that. So we're obviously not really educating people about what your options are. If that's really what you want to be, you would have signed up for the classes. You signed up for science.
I'm just kidding.
I just feel like.
Remind me where we left off. We still have, tomorrow we have to talk about, I guess we've got out of time. Tomorrow we have to talk about bond energy, so you remind me of this. I think that's it. Bond energy is what we're gonna talk about tomorrow, okay?
Hey, Mr. Cato, when do you think this testing will be in grade?
I might get to start working on that next year.
Yay!
That doesn't mean I will finish.
See?
Which means I'll get started.